Welcome, everybody. My name is Yanan. I'm a solutions architect at AWS. At work, I help enterprise customers build their cloud-based solutions. But at home, I'm a father of two, and extra helps are always welcome. So I get robots to mow the lawn and clean the floors. Certainly, it's not because I'm lazy. And so today we will talk about robots made better with AI in cloud. And we will cover several topics, some robots for home, and how do they work, some limitations I found, and how can we make them better with the cloud, some challenges, and finally a survey, which is very important for me to make my slides better. Okay, let's start. Let's start with robots for home. So my first question is, anyone here own a robot or more? So let's do this. If you have one or more robots, you can type one in the chat. If you plan to have more, have one, at least one in future, you can type 2. And if robots is not your thing, please type 3. And if you think you are a robot, then you can type 4. Okay, I'll stop share and I'll see the replies. Okay, we have a fair amount of people who have robots. And we also have a robot. Okay, nice. Oh, I actually can see the chat. So, okay, the first kind of robot, they do the cleaning. This is one I have. And also some robots, they work in the garden. And there are also robots as companions and some others. They're for education, like this Now robot. It's a humanoid robot called Now, which is very popular. So the question is, how do they work? And let's take the robot cleaner as an example because it's the most popular one. And also we will be focusing on the robotic parts, not the parts like the vacuum machine, how do they work, and also how do they clean the mops automatically, which actually some robots do. So this is a robot. As mentioned, I use this. And let's take a look. So in the front, we have a camera. So it's a top-mounted camera for visual SLAM. It's also called a VSLAM. And then in the front, this circular thing is called a contact bumper. Actually, it has several spring-loaded switches, and everything when it bumps into something, the switch gets triggered. So as they may have more switches, so they will know whether left or right gets bumped. And if you notice, there's also a black cover, and actually under that cover, there is a set of sensors, normally called proximity sensors, usually are IR sensors. So they help the robot to detect things that's close in the front. And the cover is there to help to filter the ambient light to make the sensors work more efficiently. Let's flip over the robot to see what's on down there. So from the bottom, you can see there are more components like these. So there's 4 of them. These are called clip sensors. So they are distributed around the robot to prevent the robot falling from stairs, for example. And as it's a cleaning robot, so there's a brush. The brush helps the dirt to move closer to the vacuum cleaner. So that's a vacuum cleaner. And this robot also features a pair of mops. Then a set of wheels, which can spin independently. So the robot can move into any directions. And also, don't forget, there is a caster wheel, which is to supporting at the third point of support. Okay, the last one. Oops, I clicked it too quickly. So the last one, under the wheel, there are four lights. So can you guess what it does? Type 1, if you think it's a material detector to identify hard floor and carpets. Type 2, if you think it's a dust detector to verify the effectiveness of cleaning. Type 3, if you think it's an optical flow sensor for tracking the odometry. Okay, please type. 4. Okay, you think differently. All right, so for this one, it's actually a optical flow sensor. So what it is, it's some people just call it a mouse sensor. So that's much easier to understand. If you use an optical mouse, it's basically the same thing. It helps the robot to track its odometry, including position and also orientation. Yeah, the circle should appear first. All right. So we will be covering the elements or the components robots have. Now let's take a look at the navigation methods. How do they go around and how do they navigate? Let's take the first one as an example. I call it dumb because it's quite simple. A dumb robot only needs to know three things. The first one is when I hit something, I turn to any direction and keep going. Two, I need to go back for a charge because my battery runs out. Three, how to locate the charging station. Usually it's a stationary object shining IR lights, so the robot will try many times until it finds a beacon in direct sight. So this is how it navigates. As you can see, it may go to anywhere, but eventually it will cover almost all the areas. So the dumb robot doesn't need to know the environment at all, and it only responds to simple changes. For example, it bumps into something. They don't really plan. They will go a straight line until they hit something, then turn to a different direction until some time is passed or they have to charge batteries. Unlike the cleaning robot, which work indoors and they have walls or boundaries, and they won't go to the wild, the robot lawnmower will need a closed loop of electrical wire to keep it inside. It's called a boundary wire. Because the garden could be much bigger than the area of the house, they usually have a guide wire which to help them return to the charging station. So there's a major difference for indoor and outdoor. From the look of it, it doesn't look very smart, but the this technique is actually quite effective and very mature. Nearly 100% of the robot lawn mowers on the market today are using this method, even if it costs you, let's say, $1,000. Okay, let's take a look of another popular method, which is called SLAM. SLAM stands for Simultaneous Localization and Mapping. The robot is able to build a map of an unknown area, and it's capable to estimate where it's located. This way, the robot can plan the route more effectively. Before we look into how the robot use uh, SLAM, let's take a look of the data. Even if we use the best components money can buy to build the robots, the data we have will still be noisy. It's just the fact how this world works. So let's take a look. For example, some robots use LiDAR to scan the environment. They don't get perfect readings, and in fact, the dots from the sensor may not in a straight line, not to mention the noisy images from the cameras. And also the way used to update the odometry, like optical flow sensors, is not perfect. The tracked positions may vary and it may be deviated from the actual positions. Well, let's take a look how robots handle these during localization and mapping. First, assume the robot already has the map. Then let's take a look how the robot will locate itself. A popular method is called particle filters. Here, we will only cover the basic concepts. We will not deep dive into the mathematics. The goal is to get a high-level idea of how it works. Let's start. So in the beginning, the robot knows the map, but has no idea where it is. Since the robot knows nothing yet, let's assume the robot could be anywhere in the room. So we randomly created some possible positions of the robot and make sure they are equally distributed in the room. Next, we will also rotate them randomly, but also make sure the rotations are equally distributed. These estimated positions and poses are called particles. The more particles we have, the higher accuracy the localizations will be, but it will take longer time to compute. So there is a trade-off. Here we only create 21, but in real world, you may need thousands or more. To tell where the robot is, we need to do some measurements. In this case, our robot features a LiDAR sensor, so the sensor can scan the surfaces and return an array of readings. Next, what we will need to do is to compare the readings to all the possible readings from the particles. And by comparing them one by one, obviously some are less similar and some are more similar. So we assign these particles with different probabilities after this round of comparison. And the bigger the possibilities, so we put them bigger. And if they have smaller possibilities, then we shrink them. So that means they are less likely to be there. The next step, we will remove the less likely particles from the list. And the remaining particles may not be the exact location of the robot, but they represent the likely area. So the next step is we will create more particles in the more likely areas. And we will let the robot to move again. So we will get different readings. And we will also use this information we tracked from the internal odometry to update these particles inside of the robot, and we will compare the LiDAR readings to the estimated readings from the particles and repeat the process until it converges to one highly likely area. And in this way, we can localize the robot. Okay, now we can localize the robot. How about we don't know the map? So in this room, there is a box. It's kind of the only feature of the room. So initially, the robot can do a scan. And in a perfect world, with perfect odometry tracking and perfect LiDAR readings, the robot can do a full scan of the room, and that's it. It will have a perfect map. All the dots, all the readings are fully aligned. But remember, we have noisy LiDAR readings and also noisy odometry tracking. So in reality, it looks like this. So we get our initial reading. Things look nice at the moment, but when we move, the gray one is the one we tracked internally, and that's how it mapped to the real world. And you can see the new readings are deviated from the reality. And this situation goes on. For example, this corner is also off, and on. However, we realize there are relationships between all these estimated position or poses. For example, for one pose to another, there is a certain amount of distance traveled and also an orientation change. So we link them together and create a pose map. And as we do more of these, we can create more bounds and more poses. Until one moment, we keep doing this until one moment, you realize the last one, it looks like it's facing the same direction. And in this case, actually, it is detecting the same set of features which we have been recognized before. So, and we are quite sure that this is the same feature we have seen. So we can close the loop. And now we know how to adjust the whole chain of relationships by changing the distance and also orientations. And in this way, the pose graph converged, and we can update the bounds between all the poses and optimize the map. And this process is called pose graph optimization. And this process can continue to create more bounds and to further optimize the map. All right, so we covered the main pieces of SLAM. And next, let's talk about the limitations. So we have nice algorithms which actually work, and even some robots have image recognitions to identify obstacles. But the robots, they have major limitations. And before we dive into those, let's take a look of a video clip from here. And in this video, this flagship robot is performing its daily routine. All right, so we see the robot just paused there for several seconds. What do you think? What's your opinion about this behavior? What's it doing? Type 1, if you think the robot is tired and it needs a break. Type 2, if you think the robot needs to recover from a bump. Type 3, if you think the robot is doing some intense computing. What do you think? Great. It seems the audience do have the same opinion. Exactly. So my initial guess was the robot paused to take a photo and use ViroSlam to localize itself. But I wasn't quite sure, so I did the following experiment. And to verify my guess, I covered the robot's camera, so it's blind. But as you see, it's blind, but it was still able to navigate. So rather than performing ViroSlam, the robot chose to rely on its optical flow sensor to keep the odometry. The reason seems simple when we take a look of the CPU it's using. So the robots are mostly battery powered, which means they need to consider the battery capacity and they work in a power efficient manner. However, power efficient usually means less powerful. And remember the two tasks we mentioned previously, and they are kind of compute intensive. And when using single camera visual SLAM like that robot, higher accuracy requires a lot more CPU power and bigger memory capacity to process the data. For example, Dyson's latest robot vacuum has 10 gigs of onboard memory. And this is a popular 4-core ARM CPU. The model number is R16. It can be found in many robot cleaners like some models from Xiaomi. And even today, it's been out there for many years. It's still that popular. And how about we do a comparison in the cloud? And to be fair, in the cloud, apart from the x86 CPUs, there are also ARM CPU options like Graviton 2. And this is the latest ARM CPU from AWS. It's a purpose-built CPU for handling extensive workload in the cloud. And this CPU supports up to 64 virtual CPUs. Next, we'll see a benchmark of how they perform. But to make it a fair comparison, in the benchmark, a type of compute instance called M6G X large was used, and this configuration also consists of 4 cores, and it's 4 logical cores, the same number as the R16, and the benchmark used was Geekbench 4. So let's see the comparison. Well, it's obvious that Graviton 2 was about 10 times faster than the opponent. This is not entirely fair because R16 was made for mobile applications with power constraints, while Graviton 2 was for intense compute workload. But we can see the performance improvement when using cloud. With the power consumption limit removed, we also can use even more cores like 64, for example, or even more instances. And robot cleaners also update very frequently. Each manufacturer often release more than one model per year. For example, iRobot has 9 generations since 2002, and the robots may use different CPUs each year due to cost or performance. And if we take a look of the robot anatomy from a different perspective, all these things are fixed when you purchase one. The CPU, sensors, motors, and also the cleaning parts. They won't improve, but over the time, there will be software upgrades and security patches. And this looks a fairly complex stack of updates. And when you upgrade, you have to consider all the layers. And if we take a similar look, you will find that this pattern looks very similar to the mobile industry. Upgrades are always welcome, but maintaining the older models becomes a problem. It's like the Android ecosystem. Top manufacturers, they usually provide around 3 years of OS and security upgrades. But unlike the mobile phones, robot cleaners, they serve a different or a specific purpose. The hardware is sufficient to complete the task. So robots evolve frequently with better processors and mostly improved algorithms, but not necessarily better vacuuming. Well, the shorter support window also means there will be no more firmware updates, which can leave the robots in a vulnerable place. If new exploits were found of the older software, then it may highly likely that the manufacturers won't even fix these because there are just so many old models and varieties. If you remember the famous Heartbleed security bug from OpenSSL, there were so many hardwares left in the wild without any fix. And think about the environment impact. If we upgrade so frequently, that's no good. The third point is there's no teamwork. And we haven't seen robot cleaners work as a team yet. There are some experiments out there, but it's mostly to put the robots in a queue, but none of them allow the robots to work in parallel. It's necessary in a way. For example, when you have only one small area, it's okay to have one robot to do the whole job. Even it needs to recharge for several times. But how about the area is so big? It's just not enough for one robot to cover. It's more likely that a single robot won't do this efficiently. And then we will need more of these. And to achieve this, the robots will need to communicate to each other and also to share the knowledge. For example, where I am and which areas are being covered already, so I won't cover that. And also, they can schedule the work more efficiently. So as mentioned, nothing's really achieved yet, even for industry cleaning robots in this area. So I love my robots, and I can't stop thinking how to make them better. In this case, maybe let's use a bit help from the cloud. The idea is to move the intelligence into the cloud. A robot can keep its map and algorithms locally, but due to CPU limitations, it may not be running at its full potential. With the limited power, compromises has to be made, such as a reduced data resolution, reduced localization frequency, just to make it easier for the robot. But what if we can move this constraint by using cloud? Then offload the compute-heavy tasks to the cloud. Then the next step is to make the cloud as an extension of the robot by implementing a protocol. And then we can connect the robot to the cloud via internet. This protocol implements a secured connection. The robot sends sensor data like LiDAR measurements, camera images to the cloud, and the cloud will tell the robot where it is and where to go. This way, we decouple the robot brain from its physical existence. And cloud can also make robots cheaper. This is a breakdown of the cost of making a robot for the so you can see majority of the cost is from material. And this is for Ecovacs. It's a very popular brand. So you also can find the source from their annual report. And they keep a margin around 43%, and the cost is 57. But if you look at the CPU, it only costs $5. Where do the costs go? So to make the robot cheaper, let's look at it from a different perspective. With this decoupled design, as we mentioned, to move the algorithms into cloud, it actually helps the manufacturers to save cost. Because now the robot is cheaper to develop. Since they will be sharing a unified platform, there is less complexity on the robot itself. The robot will even be cheaper to manufacture because they don't need to use expensive CPUs or use large batteries. So it's cheaper to make. And more importantly, the robots now they are less complex. So there will be fewer problems. And that means the robots will be also cheaper to support. These benefits will also be passed to the consumers. And we also can make the robots better. So for the manufacturers, for the consumers, the performance will get better over time because the platform will evolve over time and the algorithm will evolve, and there is no need to change the robot even for software upgrades. And the consumers can also expect a longer support lifespan. That means for the longer term, it's cheaper to have the robot. And also, because of the capability now the platform has, there will be the possibility to use multiple robots at the same time so they can collaborate. And it's also good for the environment because now there are fewer electronic wastes. And there is a major change for the manufacturers as well. From one-off purchase, which is nowadays, it will turn into a subscription model. So this opens more opportunities for the manufacturers. And also, they convert the one-time buyer to a long-term user. It creates a certain stickiness. Well, nothing comes for free. So what about the challenges? It sounds so good, but what about the challenges? The first one I can think of is latency. And because it's not reside locally, the robots will be at your home, but the processing in the cloud may be somewhere else. And we can use different techniques to mitigate this. For example, edge computing is becoming much more popular these days. There are local zones, or you can compute at edge, at the CDN edge. And instead of moving the thing, you're moving your home closer to the cloud, so we move the cloud closer to the endpoint. And we also can use optimized protocols. So there are protocols combining TCP and UDP to make the latency shorter, or to make it more consistent. And more importantly, the robot is really not a mission critical task, I would say. For example, 20 to 100 milliseconds for game streaming is considered to be good. 20 milliseconds, that's about from London to Frankfurt in Germany. And 100 milliseconds, that roughly can reach US from London. So how about network stability? Imagine there's one day that your internet is down. The robot won't work. Disaster. So my argument to this back is, can you live a day without internet? If you can't, then get it fixed. It's that easy. So as mentioned, if you can live without the internet for a day, then I'm quite sure you can live without a sparkling floor for one day. And the third thing is security. How about security? Because now we are opening the robot to the internet. And how about the hackers from the internet? How about my security? The fact is, most of the robots are already connected. And that means if you have security issues, it's already there. So this openness won't create more security issues, but it will actually improve it, because imagine we are using a open standard. Think about 3G or 4G protocols. These are standard and they are open, they are mature. So if we are using a matured standard, it actually will be more secure. And also the platform is much better and more secure than the individual firmwares. It will be an evolving piece. So in the long run, it will be more secure than the individual firmwares. All right, I think that covers everything. And so what I want to call for actions are, here are some useful links. So let me run through them one by one. So there is an interesting program called Deep Racer. So it's using deep learning to do the navigation, and also you can use this to do the racing for the cars. I find that's quite interesting. Then we also mentioned about edge computing and some IoT solutions. And as mentioned, some robots, they are already using image recognition to tell whether this is a dirty sock, should I go around it? Are these charging cables? Should I also go around of these? And how about this carpet? Should I move onto it to clean it? So it's also a very popular topic. And at the end, there are some references I find very useful. Some cover these topics in depth, like post-graph optimization, and particle filters. And there's a tear down of a robot. Finally, some papers for you to bring home to read. And the last section is, if you have time, please help me with this survey. That really means a lot to me to improve my speech. So if you can take 5 minutes to complete this, you can either scan the barcode or I'll send the URLs in the chat. So I'll quickly do that. So I send it in the chat. If you can help to do the survey, that will be great help. So that covers everything I want to cover today. And thank you very much. Thank you. I'll keep sharing this and I'll bring up my camera. And if you have, I think we still have plenty of time and we can have 5-minute sessions for Q&A, which wasn't planned. If you have questions or ideas. So the first question, does the autonomous navigation run in the cloud? Yeah, you can imagine that we just bring that part in the cloud and it will be the same algorithms. It's just to build that protocol, that interface to decouple the software. So there are many ways to run it. So what I can think of, any books, is we can either use traditional resources like virtual machines, and you also can use containers. Alternatively, I was thinking to use even serverless like Lambda. So you can write Python or JavaScript or any other language, but it will be more cost efficient. Any books or resources we can look at for, yes. So I think a good starting point is I will share these. So share these links with you. So that will be a good starting point. Then you can explore more. Okay, I will stop sharing and bring back my camera. And will you be sharing the slides? Yes, I'm okay to share the slides. The slides are made for you. Any more questions? Or challenges? What would be the good starting point of robotic AI navigation for beginners? Yeah, I think I'm not the best guy to recommend this, but from my point of view, it's really good to look at this MATLAB series. So you even can do that in a controlled environment in the simulator. So that will be easier for you to start. So you can see how the robots moves in the simulator and have a more intuitive understanding. How is GPT-TPU involved in this? So yeah, that's a very good point. So for example, if you want to utilize machine learning powered navigation, there are actually out there. So machine learning can be optimized using GPU. It will run much faster. So it's like running your inference workload in the cloud. So there are dedicated GPUs, the enterprise grade like NVIDIA V100. It's more powerful than the gaming rigs we usually have. And also from the cloud, there are also dedicated instances for inference. So it's like a bespoke chip for that purpose. But it's a very advanced topic, I would say. Is there any role for deep learning? I don't quite understand. Are you asking for jobs? Wondering, would a hacker hack in robot? And I think that's a possibility. It's like hacking into the webcams. Remember, there was a popular the period in the history that the passwords were all about admin. So a lot of cameras were hacked. So I think that's a possibility. When will robots and AI be in law and the justice system? I don't know. I'm not the best at the best position to answer this, but that's a very interesting question. Probably there are. What if they are already using it for cleaning the floor? Can we say it's in the law and the justice system? I think at least you can use it to train the lie detector, for example. Do you believe AGI can be achieved? I don't quite understand AGI. What is it? That's where I'm going to. Okay, share links and URLs. How about a robot that is multifunction, cloud and local? Yes, that's a very good point. So imagine if we want to process the bumper request, you want it to act immediately. So it's very similar like how our brain works. So the brain has several parts. One is for more logical functions, but the other is for immediate reflexes. General intelligence.
Great. I guess this are this much questions. Thank you, Yanan, for your time. Appreciate it. It was very good. I like that. It was very clear.
Thank you.
And hopefully everyone enjoyed. Everyone, thank you for participating in the event. So please tune in for future events. And we hope to see Yanan in our future events as well.
Thank you very much. Remember to do the survey.
Yeah, please. Thank
Thank you
you.
so much.
Bye.
Bye bye.
Bye.